Hey friends. Okay, so now we're going to begin lesson 3. Yesterday, or in our last lesson, depending on the last time you listened to me, in our last lesson, we talked about the derivative of sine and the derivative of cosine, and we figured out that the derivative of sine was cosine and the derivative of cosine was negative sine. And then we worked through questions on just looking at other derivatives, knowing that piece of information. So today we're going to expand on that knowledge, and I'm going to give you a bunch of other derivatives that will be on your formula sheet. Okay, so this formula sheet is going to be like super important to you. You're going to want to refer to it a lot as we go through the next few lessons. Just like with 30-1, that formula sheet became so important to your life when we did trig. Same thing here with calculus. The formula sheet becomes super important for you to reference as we go through trig, okay? And so essentially what we're gonna do is we're gonna look at these 6, and we're gonna work with these 6. Now I've already given you the first 2. The derivative of sine was cos, and the derivative of cos was negative sine, okay? For fun, it would be neat if you could take all 4 of these other ones and see if you can make this happen. Change them to sine and cosine, and then take the derivative based on your sine and cosine equation and see if you can come up with these guys, okay? I'm going to do 2 of those for you. I'm going to do tan x, and I'm going to do cosecant x, just to show you what I mean. And then I'm just going to leave secant and cotangent for you to try on your own. You know what the answer should be anyway, so I think you'll be okay. But just to show you what I mean, everything's derived from things we already know, right? So if I had been looking at y equals tan x, and I wanted to take the derivative of that, well, what I could do is say tan is sine over cos. So I could say that sine x over cos x. So now if I want to take the derivative, I'm going to go, hey, that's the quotient rule. So I'm going to go derivative of f times g minus f times derivative of g all over g squared. So the derivative of sine, that's my f, derivative of f, sine is cosine, times g, minus f times the derivative of g. Well, the derivative of g, the derivative of cos, is negative sine. Okay, and then all of that's over g squared. So it would look like that right now. Okay, now cos times cos would be cos squared. Negative sine times negative sine would be sine squared over cos squared. So now that gives me 1 over cos squared, and 1 over cos squared is secant squared, which is what is on your slide right now. Okay, so using just what I did yesterday, I can prove that, yes, the derivative of tan of x is secant squared of x. Okay, now the point is, given that that's on your formula sheet, you can jump right there. Okay, I'm not asking you to do this every time. I'm asking you to use your formula sheet, but I'm trying to show you that we don't just make this stuff up. We're deriving it from stuff that we already know. Okay, I'm going to do one more with you, and that is cosecant. Okay, so I'm going to start with y equals cosecant of x. And I know that y equals cosecant of x. Cosecant is 1 over sine. And so now I'm going to write that as sine x to the negative 1. Okay, so now I'm going to take the derivative of that. When I take the derivative of that, I have the chain rule here. So that's going to be negative 1 sine x to the negative 2, right? The negative 1 comes to the front, and I drop down a degree. Then I have to take the derivative of the inside function. The derivative of the inside function, well, the inside function is sine x, so the derivative of that is cos x. Okay, now that leaves me with essentially y equals, I'll write it like this first, negative cos x over sine squared x. Okay, my sine x to the negative 2 would come to the bottom, and then that would be sine squared x. okay? But now I'm just gonna simplify that a little bit, and I'm gonna write that as negative cos x over sine x times 1 over sine x. Okay, I just kind of split that sine squared x into two different sine x's on the bottom, because I see cos over sine is cotangent, and 1 over sine is cosecant. So I end up with negative cotangent x cosecant x, which again is what is on your table there. I just don't have it in the exact same order, but in multiplication, that doesn't matter. So, okay, so I've proven 2 for you just for fun. You can try the other 2 on your own time if you like, but that's all we're going to do today. Is we're now just going to work with not deriving them, but we're going to work with actually finding derivatives using the stuff now that's on our formula sheet. Okay, so I want your formula sheet out and handy. If you don't have one, you can get one off D2L. If you can't find it on D2L, you can email me and I will email you a copy. Okay. Okay. So big thing before we begin here that I need you to focus on, because this is just a common mistake that is made. Tan of x squared is not the same as tan squared of x. When we see tan squared of x, when we see the 2 on, sorry, I'm just trying to get ink on here. When we see the 2 on tan, what that means is there's a square on whatever tan of x is, okay? Not on what x is. And you're gonna see both, so you gotta know when you change it to there's a square on everything and when there's just a square on the thing you're taking the trigonometric function of, okay? Okay. So here's our first one, determine the derivative. Okay, so I've got 1/2 tan of 4x. Now, I go to my formula sheet, I know that the derivative of tan is secant squared. Okay, so the derivative of tan of 4x will be secant squared of 4x. Then I have to take the derivative of the inside function. So I end up with 1/2 secant squared of 4x, and then the derivative of 4x would just be 4. And that's why there's a 4 on the back there. So then I'll clean it up slightly. I can do the 4 times 1/2, and that will leave me with 2 secant squared of 4x. Okay, secant squared of 4x. Okay, next guy. Again, you probably want to start pausing me and trying these on your own before you see me do them, okay? Y equals secant squared of the root of x. Okay, there's a few things going on here. The first thing I know what the derivative of secant is, but I've got that square to deal with. So that square is on the whole thing. So first of all, I'm going to rewrite that as secant of root x all squared. Okay, now what kicks in here is the chain rule. The 2 comes to the front, and then I drop a degree. So that's going to be 2 times secant of root x to the 1, essentially. Okay, then I have to take the derivative of the inside function. Currently, the inside function that I'm looking at would be secant of something. Well, the derivative of secant is secant, the derivative of secant x. I'm just reading it directly off the formula sheet. That's why you saw my eyes dart down. You know what I'm saying. The derivative of secant x is secant x tan x. So the derivative of secant root x would be secant root x tan root x, okay? Then I have to take the derivative of the inside function, which is the root of x. Well, you know that the root of x, this is way back to the second unit, the root of x is x to the 1/2, so the derivative of that would be 1/2 x to the negative 1/2, okay? And so that's everything I've written here, okay? The 2 came to the front, my secant root x dropped to a degree of 1, then I had secant root x derivative. The derivative of that would be secant root x tan root x. And then the derivative of root x was 1/2 x to the negative 1/2. Now, to clean this up, you gotta be super careful when you're cleaning this up. You can, like, for instance, I am multiplying secant root x times secant root x here. So I can call these guys secant squared root x, right? An x times an x is an x squared. A secant times a secant is a secant squared. You got to be careful before you do that, though, that it is actually two trigonometric functions, okay? What I mean by that is in other times you might see secant of tan root x. Well, that's something very different, right? The reason I can multiply these both together here that I've underlined is because they're both secant of root x. So secant of root x times secant of root x will give me secant of root x all squared, okay? Then the 1/2 can multiply by the 2, so that's just going to be a 1. And the x to the negative 1/2 will be root x on the bottom. Okay, so I believe I have everything cleaned up there for you. Okay. Sorry, let me take, okay, now this is the example that I was just talking about, okay? Lots of kids look at this and they immediately start thinking, oh, I have to do the product rule. Be careful, no you don't. This is not cos x times tan x squared. It's cos of something. You see that? There is no other x there. You're taking the cos of tan x squared. So this is not two separate trigonometric functions that are being multiplied together. Tan x squared is actually the input for cos of x, okay? So we've got a couple layers of the chain rule that we have to deal with here. First outside thing I see is cos of something. Well, the derivative of cos of something is negative sine of that something, okay? So that's gonna be negative sine of tan x squared. Then I have to start taking the derivative of the inside function, which is tan of something. The derivative of tan is secant squared. So that's going to be secant squared of x squared. Then I have to take the derivative of that inside function, which is x squared, and that'll be 2x. Okay, so when I write all that out, here's the negative sine tan x squared, because that's the derivative of cos. Inside I had tan x squared, the derivative of tan is secant squared, so that's secant squared x squared. Then I had to take the derivative of the x squared, which is 2x. Okay, now there's not a whole lot I can do to clean this up. I'm just going to move my 2x to the front, essentially. Okay. All right. Kill the ink there. Okay, negative cotangent of x minus 1 all squared. Again, here's another example where that square is not on the whole thing. It's not on the cotangent of something. It's just on the x minus 1 of something, or the x minus 1. I guess I didn't need to say the of something there. Okay, so what do I see? Well, I see that I have to take the derivative of the cotangent of something. The derivative of cotangent is negative cosecant squared. Okay, so I'm going to have this negative in front, and then I'm going to have negative cosecant squared of x minus 1 squared. Then I have to take the derivative of the inside function. Well, the derivative of the inside function, that's first of all the chain rule. So that's going to be 2x minus 1 to the 1. And then the derivative of that inside function. But for this guy, that's just going to be that inside function is just x minus 1. And the derivative of that would just be 1. Okay, so again, just for clarification, here's my negative. The first thing I did was I went cotangent, the derivative of cotangent of something is negative cosecant squared of my something, okay? Then I took the derivative of x minus 1 squared, which is 2 times x minus 1, times the derivative of that inside function, which is just 1. So I've got a negative times a negative, so overall my answer will be positive, and I'm going to move that 2 times x minus 1 up to the front. And so I'll be left with 2 times x minus 1 times cosecant squared of x minus 1 all squared. I should not have said all squared there. I meant x minus 1 was all squared. I just don't want you to get confused with my wording. Okay. Cosecant squared of x minus 1 squared. Okay. Okay. Isn't this fun? Okay. Let me kill the ink. Sine of 3x over tan of 3x. Now, personally, I would probably want to see if I can simplify this guy before I start calculating the derivative of it. Okay, if you want to do it now and you want to use the quotient rule, go ahead. I'm just going to take this and I'm going to say, okay, well, I know that tan is sine over cos. So I'm going to write this as sine of 3x divided by sine of 3x over cos of 3x. Then I can see that that's going to be times cos of 3x over sine of 3x. And I know that my sine of 3x's will divide each other out. So I'm actually just left with cos of 3x. To me, it's much simpler to take the derivative of this than to use the quotient rule up here. Okay, and I know that the derivative of cos of 3x, well, the derivative of cos, I'm having a hard time saying the word derivative today. The derivative of cos would be negative sine. So my answer for the derivative would be negative 3 sine of 3x, because I also have to take the derivative of the inside function there. Okay. Awesome possum. All right. Determine the equation of the tangent line to the curve y equals sine x tan of x over 2 at x equals pi over 3. Okay, well, if I want the equation of the tangent line, the first thing I need to do is figure out the slope, and to do that, I take the derivative, right? So I'm looking at taking the derivative of sine x tan x over 2. That is the product rule. That's f times g. So the derivative of f times g is the derivative of f times g plus f times derivative of g. So that's what I'm going to go through. The derivative of sine is cosine times g, which will just be tan of x over 2, plus f, which will be sine x, times the derivative of g. The derivative of tan is secant squared. So that'll be secant squared of x over 2. Okay, so I just use the product rule there. Now, there's nothing really I can do to clean this up. I'm going to move my 1/2 up to here just so that I've got the coefficient in front of the term, but that's actually all I did there. Okay, so now this represents all tangent lines of the original function, right? I want the specific slope. Sorry, I just want to back that train up for a second. This represents the slope of all tangent lines along that function. Okay. Now I want the specific slope when x is pi over 3. So I'm going to plug pi over 3 in for my x. So this is going to be cos of pi over 3. This is going to be tan of pi over 6 because pi over 3 times 1/2. This will be sine of pi over 3. And then this will be secant squared of pi over 6. Okay. Now I'm just going to take that bottom line and stick it to the top. I haven't changed anything here. But now I just have a little bit more space to work. Okay, so I know that the cos of pi over 3 is 1/2. The tan of pi over 6, remember that if you think back to your 30-1 days, tan is your y value divided by your x value. Okay, so that'd be your sine divided by your cos. So tan of pi over 6 ends up being root 3 over 3. In an unrationalized form, if you were looking at your formula sheet, I don't know if you've noticed, but it actually tells you for sine and cos, it tells you some of the exact values from your trigonometric or from your unit circle. Okay. So remember that if it's sine over cos, you're taking 1/2 and you're dividing by root 3 over 2. And that would give you 1 over root 3. Okay. And then I just rationalized it to the root 3 over 3. Then sine of pi over 3 is root 3 over 2. So I've got 1/2 times root 3 over 2. And then secant of pi over 6 squared. Well, the secant is the flipped version of cos. Cos of pi over 6 is root 3 over 2. So if I flip that, that's 2 over root 3. And then if I square that, that would be 4 over 3. Okay. So now I'm going to just start cleaning up the math a bit here. This is root 3 over 6. This would be 4, actually 2 times 2 is 4, so my 4s are gone. So this ends up being root 3 over 3. Okay. I did the multiplication here first, but I'll simplify it. So root 3 over 3, sorry, I can't talk today. 3 root 3 over 6. And then the 3 over 6 actually reduces to root 3 over 2. So I end up with root 3 over 2. The slope of my tangent line at x equals pi over 3 is root 3 over 2. Okay? Okay. Now, I need to build an equation. You were asked to determine the equation. I know my slope. I know my x value of my point. In order to build an equation, I need the slope and I need a full point. So the next thing I need to do is get my y value of my original equation. Okay, so I'm going to take my pi over 3. I'm going to plug it into my original equation, which is y equals sine x tan x over 2. And then that ends up giving me root 3 over 2 times root 3 over 3. And that actually simplifies to 3 over 6, which is 1/2. Okay, so now I know I'm going to build an equation that has a slope of root 3 over 2 and passes through the point pi over 3 comma 1/2. Okay, so I'm just going to go to slope point form. Y minus y1 equals m times x minus x1. And so there's my equation. Okay, y minus y1, my y1 was 1/2 times m, that's my slope. And x minus x1, my x value of my point was pi over 3. Now, I don't care what form you write the equation in. So if you want to write it in point slope form, if you wanted to have written it in y equals mx plus b form, that's cool. Or if you want to go all the way and take it to general form, that's cool too. Okay, it has to be one of those 3 forms done correctly though. Okay, awesome. So that's what you're doing today. Here are the pages that we're working on. And if you have any questions, you know where to find me. Okay, we'll see you for lesson 4.